Yeah, so thanks everybody for assembling back after lunch. So I think the treat continues after morning's excellent presentation by Nico here, and also very active, lively participation from the young audience, who I wish will also equally probe the current speaker, because he's really an expert on what he's going to talk. Ultrafast molecular fragmentation dynamics. Professor Shankar Dey is a faculty member at the Shah Institute of Nuclear Physics in Kolkata, and co-affiliated with the Homi Bhabha National Institute University. Professor Dey, of course, he is no stranger to us in this community, but for the young folks who are here, you did your PhD, sorry, I forgot. Where did you graduate with your PhD from, Shankar?
Inter-University Accelerator Center?
At the IUAC Center. And then he did impressive postdocs, but I know him more from his papers and meeting Shankar at conferences and at institutes, and from the fact that he's an expert on photoelectron, photon spectroscopy, spectroscopies rather, and coincidence measurements, about which Shankar will educate us a lot. And also from his current interest of active research, which is in quantum optics and quantum spectroscopy, about which we will have to invite Professor Shankar for another different visit to hear more about. But for today, it's about ultrafast fragmentation dynamics. The modality is the same. It's really a conversation between the expert speaker and all of us on this side. So you're welcome. And for those who just joined us, please ask as many questions as possible. We are keeping track for the best participant prize, which I promise will be given at the end of this workshop.
The same chocolates?
Two chocolates. The chocolates with special ingredients are over, so we will bring something else. Shankar, please. Thank you.
Thank you, Shiva, for this nice introduction. Yeah, after my PhD, I did my PhD in collision physics in Inter-University Accelerator Center. And of course, I was a student of Calcutta University. And then for the postdoc, I was in Kansas State University for 2 years and in Aarhus University, Denmark for 1 year. So that's on ultrafast science with femtosecond lasers. So this is a nice opportunity that Shiva gave me, like 2 hours. Now it is 1.5 hours. Hardly that I get in any conferences to present my work, so I will present rather a long thing, but I will try to make you interesting and try not to make you asleep. So I start with this. This is our institute in Calcutta, and this is our auditorium. And as you can see, I will be talking about ultrafast molecular fragmentation dynamics with ions, and later on with femtosecond lasers. So we start with ion molecule collisions. So what exactly that do we try to find out from ion molecule collisions? There is always an arrow. Yeah. So in ion molecule collisions, we want to study about the structure and dynamics of atoms and molecules. And the relevance can be atmospheric or stellar, even biological processes. But that's not actually what we do. We do just because we want to know about them, their fundamental interactions with probes. And in this case, it might be photons, electrons, or ions. And so what we do is that we study these processes by spectroscopy or by collisions. Finally, what we want to tackle is a quantum many-body Coulomb problem, because it's electrons, nucleus, and as you go bigger and bigger in molecules, the complexity increases, as my previous speaker has said. Like, even for a theoretician, it becomes really hard, and you need computational skills to find out the finer details from that. So we are dealing with this quantum many-body problem, and what we do here is that we shoot a beam of particles, ions in this case, which crosses a collection of target molecules in vacuum. Okay, and after the ions actually interact with the molecules in vacuum, we usually try to find out a single molecule condition, single molecule collision conditions, just because we want to have a detail of every single molecule. So the vacuum is necessary, and we go to really down in the vacuum of 10 minus 8 millibar, just because the mean free path is so high that at that vacuum you only have one ion colliding with one molecule. That is necessary to dissociate one molecule at a time and record the event. So this is to get finer details of each molecule one by one. You have to have collisions or colliding your ion with one molecule, and that is we call as the event. As we progress, I will explain you further. What happens there is a Coulomb interaction with the electrons in the molecules, and it changes the path of the ion. So ion nuclear interaction here is neglected, and what we do is that the electrons in the molecules get rearranged without changing anything in the nucleus, because the energy is not that high that we probe through the nucleus. And finally, what we do is we perturb the atoms and molecules as targets using highly charged particles or photons. So I'll cover both of them, and you see that how things become very different from one case to the other. Fine, and the perturbed molecules doesn't stay like that. The perturbed molecule responds to these stimuli, and then it leads to rearrangement of electrons and nuclei. So you see here that this rearrangement you will see how this rearrangement leads to different kind of phenomena, in not really in a spectroscopic sense, but more for the excited levels. And the excited levels, the ionized excited levels, are not the molecules that you have handled or you have spectroscopically studied, but rather they are different. And how different they are, how do we probe it, is all what we want to see here. So in the ion impact, if you take a highly charged ion, say argon 8 plus ion, it does generate a strong electric field. If you just calculate, this field is as strong as 10 to the power 16 or 10 to the power 18 watts per centimeter square. And this magnitude of this electric field is comparable to intense ultra short laser fields. Why you need this laser fields? Because you have to break away the bonds, you have to knock out the electrons. So the field has to be very strong so that you probe inside and get the information that what is happening to the molecules. And these fast, highly charged ions, this is HCI, which we call molecule interaction, is a unique probe, because see, for say like 1.2 MeV argon 8 plus ions passing through a molecule which is at the order of dimension of a few Armstrong. Okay, the interaction times are in a few attoseconds. If you can calculate, it's probably will be some tens of attoseconds. Even if you are slowing down by order of 1 order of magnitude, it might reach just about 100 attosecond or even not there. So in this few attosecond time scales, the molecular structure is almost like frozen. So you have a complete Frank Condon excitation here for ion impact over here. And what happens is that with an ion impact or an ion collision with this charge particle interaction, range of energy and momentum transfer is possible. That depends upon the impact factor. So you cannot really hold an ion, or there is a size of the ion that is colliding with a molecule, and at every impact factor, the momentum transfer to the molecule, as well as the energy transfer, as well as the entire dynamics completely changes. But you do not have a handle of that, because you cannot really pinpoint directly that my impact factor will be there this much. So it's a whole range of interaction strength that we could see in such molecules, which is not the case in case of lasers, because in lasers you have a photons and every photon has energy. So the molecule can absorb one energy at a time, one photon at a time, but not in case of ion impact. And there are mainly two steps here. One step, in the first step, the electron removal from fixed in space molecule at equilibrium internuclear distance of the neutral molecule. That is, when an highly charged ion interacts with a molecule, first step is that the electrons are getting removed, but at equilibrium internuclear distance. And then what is left is a highly charged entity. So the highly charged entity will try to break apart, and that happens when you have, so the next part will be the nuclear motion, which is driven by strong mutual repulsion of the generated positive ions. This we called as Coulomb explosion. So there are two steps: that you interact with the molecule, you take away a lot of electrons out of it. Actually, the highly charged ion, what it does is that if the energy is balanced with the energy or with the velocity of the outer shell electrons and the velocity of the ion is balanced, then the ion, since it is highly charged, so it has a lot of electron less, it will take away few electrons from the outer shells. And as it takes away few electrons from the outer shell, there are two things that happen. One, the molecule itself becomes unstable. There is a lot of positive charge in that, so it breaks apart. And the other way is that the highly charged ion, which is now captured electrons, say 1, 2 or multiple electrons, either retain them or leave it apart. So you can get, if it retains them, then the highly charged ion, the charge state changes. If it leaves it, then you probably get a OJ electron, or you can do an electron spectroscopy. Okay, and so you get electrons out of that. Yeah, there is no limit. I will tell you a fact that I will come to a explanation. I mean, one experimental data which I can show you. Point is that if you go higher in the charge, the electric fields goes very high. So there is a facility in GSI where they want to have fully stripped uranium. And for fully stripped uranium, you know that how many electrons it has gone out. So the electric field associated with that, there is a Bethe-Weizsäcker formula. If you go and in the Jackson, I think you can look into that and you can calculate that when a ion beam is, so this is a molecule, right? And when an ion beam is passing through a molecule at certain impact factor, it's like a certain impact parameter. It's like a single pulse of energy which is going. So it is, the ion has a lot of potential energy to that, and when it goes through, the molecule experiences a single pulse of energy, and the strength of this pulse or the strength of this electric field is like 10 to the power 18 watts per centimeter. This depends upon how charged the molecule is, what is the impact parameter, all these things. So point is, if you want to have a soft collision, like point is, if you want to have a soft collision, means you don't want to disturb the molecular structure so much, that rather you want to have undissociated molecular ions and study that, then you should reduce the energy as much as possible. For a higher energy, there are two things that happens. For a lower energy, the highly charged ion has a lot of potential energy, so it can capture ions. But for a highly charged and high energy ion, it is more of a billiard ball. So the molecule comes in, breaks the bonds, and everything falls apart. So it's critical that what is the velocity of the ions and the two processes. It's not very much a clear demarcation, but then these two processes happen probably sometimes together. So yes, energy plays a role, highly charged ion plays a role, and one data I will show you that we got something for a single plus ion but not with a multiply charged ion. Okay. And what we detect is that we detect charged particles or photons which carry the information of this response of this target. We do ion mass spectroscopy. That is because if we want to know about the fragments, we do ion mass spectroscopy. If we want to know about the electron energy spectroscopy or angular distribution of it, or we do photon spectroscopy. So these things are the response that the photons or the particles carry after the interaction. So here I'll mostly cover the ion mass spectroscopy. So yeah, if I am too fast, please stop me. Really don't know. I mean, I'm not an expert on that, but you can, if you have any idea. I mean, okay. That's a good question. I should have anyway. So while having that highly charged ion dissociated, what happens to the ions is that the excited molecule may dissociate, producing charged and neutral fragments. So the molecule after breaking apart, it has charged neutral fragments, And then the fragments carry information about the excited molecular ion. That is what I said. Now there are collision regimes which I was talking about. If you have fast ions, it has large velocity, the interaction time is short, so the transition will be completely vertical. And then it's because the target is almost frozen in time. So you can find out you can try to find out the molecular dimension or the molecular structure exactly at that moment during the interaction. For slow ions, slow means, see, the fast and the slow, these ranges are something like you can fix it with your mind. Like, so slow ions, it is low velocity, long interaction time, where the electron clouds can adjust. So the interaction that I am going to talk about, the electron clouds almost cannot adjust or adjust to some extent. But for slow ions which the electron clouds can adjust, and this leads to something called rearranging the complete molecular structure. And of course, if you go too low velocity, then you can actually study chemistry. Now, what is the information that we get out of a parent multiply charged molecular ion at the instant of ionization? Now these are a few things that you can get, and we can discuss, and we will show that exactly these points come back to you while I am presenting any data or I am presenting any results. So the first thing that comes to the mind is molecular structure, the bond angle and rearrangement. Question is, does the molecular structure that we start with in the ground state remains as that or not? Now this is important because in spectroscopy we mostly deal with the spectroscopic structure of the neutral molecule. Does that change when you go to the excited state or when you go to the ionized states? It's very tough to actually calculate those numbers also, the potential energy surfaces, the potential energy curves, but the structure in fact doesn't remain the same. Now when it moves or the structure changes, what is the bond angle between them? How the nucleus actually rearranges? You will find new molecules formed, new molecular ions formed from a molecule. So it's a birth of a molecule also happens, that completely the molecular structure changes and rearranges itself. Kinematics of molecular dynamics I will explain in the next slide, and whether that fragmentation is concerted or sequential. Means the breakup is just in one shot or the breakup has a step to it. Like this is a concerted dissociation. You see carbon dioxide, 2+ molecules, and you have all of them break up in one shot. That is, there is no in-between step between them. Okay, and there are 3 different ways it can break, with 2 ions or sometimes 2 ions, 1 and neutral. So these are the 3 different ways you can break if you have a concerted dissociation. For a sequential dissociation, you have an intermediate. So first either a neutral goes away or a charged ion goes away from the same kind of molecular ion, C2+, and then these, at the second step, these molecular ion which is formed in the first step dissociates. So either it makes C+, O+, or from C+ and a neutral O. Okay, so there are 2 steps, and it's a lot of research goes on that whether it's a dissociation, complete dissociation in one step, or it takes 2 or 3 steps. This is important. The more larger molecules that you get, the more interesting becomes all these processes. And to deal with the kinematics of molecular dynamics, over here, that what expression, what information that you get out of that. So you see here, this is a kinetic energy release. So while kinetic energy release, this depends on many other things. So you see here, let us come to this picture first. You see this is just a schematic of, say, CO separation or CO breaking apart. And this is, if you take this as a carbon dioxide ground state, then the molecule can get excited into a doubly charged carbon monoxide state, but either it can be an excited state which is ionized but it has a bound state, or it can be an excited state which has all these dissociative states. So when a charged ion interact with the molecule is excited into one of these, and these are all excited but charged states, and there can be multiple excited states. So when So when this kinetic energy means when it is ionized over here and the molecule breaks apart, that is means your CO separation goes apart, and whatever the potential energy is stored into these dissociative states or in the bound state, this kinetic energy is expressed as the energy of the two ionic partners. So if C plus and O plus are the two ionic partners, then they break apart, and from which dissociative state it has broken apart, that depends on the kinetic energy release. Okay, so how much energy does this partners take away? That exactly maps onto where these partners have originated from. Originated from CO2 plus 2 plus, that is the doubly charged carbon monoxide, the excited ones. Not only that, if you have a bound state over here, you will excite the vibrational states rather than it is dissociating, and there will be a nice at the end of the talk when I will discuss about the photon interaction or femtosecond interaction, I will say how do you really map these bound states. Even the bound states also become visible to you, and that's a very nice interesting feature. So the kinetic energy depends on the participating excited states, the overlap of the ground state with the excited state. So these two are the main things, but not only that, also to be taken into account is the fragmentation sequence, the metastability, because some ground states, some bound states may have a barrier that you can metastable, it can leak through that barrier, and the explosion geometry. That is, the whole point is that how the ion and the molecular dimension, does it play a role or not. So all these things come into the picture along with the kinetic energy, the excited state feature. And what we need is that we need the coincidence measurement of correlated velocity vectors of the fragment ions. So point is that when the molecule is completely breaking apart, unless you catch all of them, that is unless you have one molecule breaking apart and you determine all the momentum components of all the fragments from this dissociating molecule, you cannot find the correlated velocity vectors. Correlated velocity vectors will give you the structure at the moment of dissociation. So coming back to whatever we want to find out about the change in the molecular structure, the bond angles and rearrangement, or sequential and concerted fragmentation, these measurement of correlated velocity vectors of fragment ions becomes very important, because then you can track back of how the molecule was there, how does it behave while it was breaking away. And for that you need a position sensitive multi-hit time of flight mass spectrometry. Some of you have probably are working with that, some it's probably new for you, so I will go through that. So you need position sensitive because you need to have X, Y and Z, all three momentum vectors. Multi-hit means you are not looking at only one fragment. So you are looking at event by event fragment. So every fragment, if it is CO2, then you have to catch the C and both the O's. Then only you can reconstruct back the molecule, right? So you have to have multi-hit. Time of flight mass spectrometry will give you actually separate out the different masses. So this is sort of a time of flight mass spectrometer, you can see. So what you have here is that you just have, this is the interaction zone. If you look it in this picture, then what basically we have, the ion beam goes through in between the two plates and we put an electric field across it. So this one of the electric field is positive and the other is negative or zero. We call it a pusher or a puller, and after interaction, if this is a diatomic molecule, what happens is that, now see, this is interesting, is that when you break apart a diatomic molecule, the molecule can have any orientation, right? So if the orientation is along your ion, this is your ion direction, if it is along your ion, then both of them will fragment and both of them will reach the detector at the same position or at the same time. If it's an oxygen molecule, then both of them will dissociate and reach the detector at the same time. But when it dissociates perpendicular to the, say, drift tube, perpendicular to the electric field, then one fragment will go in the direction of the field, the other fragment will go back and then rotate and come back. Right? So you, depending upon this, one very important part is that you can know about which direction the fragment has gone. So the one that has dissociated along this field, exactly perpendicular to your drift field, will fall on two edges of the detector. But one fragment which has dissociated in the direction of the field, there one of them will go faster, the other one will take a longer time because it has to turn around and go. So they both will reach at the same point of the detector, but there will be a separation of their time. Okay. No, along the drift tube, then they will reach at the same detector point, but they will have separated in time. No. If you so this is a molecule. Say like these balls are from a single molecule, like this. Okay. So if it is if it is along the drift tube, so there is an electric field over here. So one of the fragment will be pulled faster. The other one has an electric field in the other direction. So it will go there, put a brake, and then turn around. Right? Arrive at different times, but at the same spot. Exactly. Exactly. And I mean, same position, but if there are two different species like carbon and oxygen, then they will arrive at two different times, but at the same position. See this. There are two different configurations of a time of flight. This is a single field time of flight. Okay, so here we do not have too much of a control of how we can. So there are other thing is that your ion beam is not exactly, or your gas jet is not exactly localized. So it has a spread to that. For laser experiments, you can focus the laser at some micron spot. So even if your gas jet is wide enough, you are still having a interaction zone which is at micron spot. But for an ion beam, the beam is probably 2 millimeter, has a diameter of 2 millimeter, and a gas jet also has a 2 millimeter. So you have a 2 millimeter by 2 millimeter and a complete interaction zone, or some kind of a cube or some kind of a cylinder where it is interacting. No, these can be really wide. So if this is like 10 centimeter, that is typically the separation that we keep. But the interactive beam, so you cannot have a very highly focused beam because you are collimated, but you cannot have a very highly focused beam. So that beam dimension and the jet dimension. The jet, if you have a supersonic jet, even then also it will have some bit of width to that. 2 millimeters, 2 to 3 millimeters beam width. Yeah. Yeah. Because you focus the laser. No, the ion beams poses a factor. Poses a problem is that when I'm discussing this part, I'm only discussing that there is one spot and the molecule is fragmenting from there. Okay, but due to this dimension, this molecule, multiple molecules can fragment over this volume. Okay, and relative to molecular dimension, that volume is a lot. So you have to, yeah, so you have to control so that you control the electric field so that the molecules which is formed either at the in any like any 2 point of that interactive volume, they should come at the same time. This is the main idea, because you see the time of flight is proportional to square root of m by q, right? So it doesn't depend on the initial position. It does depend on the initial positions, means your initial position is changed, then this peak of time of flight is also broadened. And so we have to narrow down this peak. But you cannot narrow down this peak unless you nullify the spread of this interaction volume.
So in other words, if there was the same ion present, say 500 micrometers more towards the detector, then
Yeah.
that ion will anyway reach faster. So what you are trying to do is, there will be, because of the position of Earth, there is a spread in time. The spectrometer is designed so that the broadening of this time of flight peak due to this is reduced.
This is reduced
The longitude along the spectrometer.
along the spectrometer direction. So this is, so from this single field, this is almost not possible to do. Therefore, if you use another field, a double field time of flight, which is like Welly-Maclaurin, this paper has reference to that. So if you have another field in between, which is an acceleration field, what happens is that whatever be the spread in the first extraction zone, this spread is taken care by the next field. So finally, when we reach the detector, after crossing the drift tube, this what you call this spread of interaction zone is minimized. So even if you have two fragments or molecules dissociating from either on this part of the arrow or this part of the arrow, I'm just exaggerating. So this part of the arrow or this part of the arrow, this space volume will be minimized over here. Okay? Yeah. 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 Two field always helps. Okay, so we yes. Exactly, we reduce the vacuum, we reduce the background of the vacuum so much that we only have single collisions. If we have double collisions, then this entire picture breaks down. Okay, and for getting a time of flight, we need an event. Yeah.
Is this like you're mentioning that the ion beam is having a diameter of 2 mm beam range? Like, can you reduce it to more is it possible, or it's specific for ion beam you can reduce it only that much?
So see, there are experimental parameters you have to deal with. So you can focus it with a quadrupole, sure. You cannot really focus it to micron dimensions because it's highly charged ion and there is something called as space charge effects. So it will not really focus that high. Then the other part is that the interaction, I mean, when you are dealing with event by event, molecule by molecule, and trying to catch every fragment, this is called a coincidence rate. You have to be so low in the coincidence rate, is that what he has asked, that we should not have one event interfering with the other event. So finally, we go so low in the collision rate, so low in the molecule and the ion beam number, okay, that even if you use a quadrupole, you cut a lot with the slits. And finally, you just collimate. Okay, this is, if we would have like, and the other part is that it's not only the detection of this detector is detection of this detector is the only thing. The other important part is your the electronics that will handle it. Okay, so you can have an analog pulse, and then the analog pulse you have to completely convert into digital by using constant fraction discriminator, amplifier, and things like that. Here, if you have a lot of ions coming together, the constant fraction breaks down, and it cannot identify one with the other. Every channel will have multiple ions. So you see here, there is this orange and this green. These are two different molecular partners, C and O, coming together, and they have a very small time gap between them. Now the constant fraction for every channel, the constant fraction actually has to process the orange and the green both together. But the point is that if you have too much of ions coming together, while handling one of the ion, the process for one of the ions, the other ions comes, then the constant fraction gets complicated. The dead time of these kind of detectors is like, I guess 10 nanoseconds. Yeah. This is also true for when you focus laser beam. That is true. The only way you have to focus laser beam because you have to go to that intensity. The only way to control that, you reduce your gas volumes. So you reduce your target. You cannot reduce your laser. I mean, see, the laser power is not very high, but when you focus it, you have to go to that intensity. So nothing else works actually.